Hello everyone, it is a great honor to be here and have the opportunity to make a report on our work, learned Interpretable Residual Extragradient ISTA for Sparse coding. I'm Lincoln and I'm from School of Artificial Intelligence, Xidian University. The report consists of 5 parts. Now we first introduce the relevant backgrounds, including these 3 parts. Firstly, in our work, we mainly consider the following problem, which is to recover a sparse vector x star from an observation vector y with noise epsilon. The noise here may be additive Gaussian white noise or other forms of noise. This process can be expressed by equation 1, where A belongs to the set of M by n-dimensional real numbers, which is a dictionary matrix, and the dimension M is generally much smaller than the dimension n. Thus, it is an ill-posed problem. Therefore, we need to combine some prior information, and in our work, we assume x star is sparse. For aforementioned sparse coding problem, a common way to estimate x star is to solve the following minimization problem with LE norm regularization, which is also called lasso problem. A commonly used algorithm for solving the lasso problem is iterative shrinkage threshold algorithm, ISTA, and its update rule is as equation 3. In equation 3, St theta is the soft thresholding function with the threshold theta. 1 over L is the step size. In 2010, Carroll and Yan proposed LISTA by unfolding ISTA into the form of a network. The network structure of LISTA is shown in figure 1, and the update rule is shown in equation 4, where W1t, W2t, and theta t are initialized as the corresponding value in traditional optimization algorithm. All the parameters W1t, W2t, and theta t are learnable and data-driven. Based on the above backgrounds, we propose the motivation of our work and we summarize our main contributions. We find that all the existing variants of LISTA with convergence guarantees are zero. The residual network ResNet, which is influential in deep learning, has not been introduced into LISTA. An important reason is that changing the original structure of LISTA will destroy its excellent mathematical interpretability. Can we get a new LISTA with an interpretable residual structure which has a convergence guarantee? The main contributions of our work are listed as follows. We propose a novel unfolding network named the Extragradient-based LISTA ELISTA, which is a variant of LISTA with residual structure by employing the idea of extragradient into LISTA and establishing the relationship with ResNet, which is an improvement about the network structure for solving sparse coding problems. To the best of our knowledge, this is the first residual structure LISTA with theoretical guarantee. We prove the linear convergence of ELISTA. Moreover, we conduct extensive experiments to verify the effectiveness of our algorithm. The experimental results show our ELISTA is superior to the state-of-the-art methods. Next, we will start to introduce our extragradient-based LISTA algorithm, ELISTA. It consists of 3 parts. We know that ISTA can be treated as a proximal gradient descent method. Therefore, we consider whether the idea of extragradient can be introduced into ISTA. The extragradient method was first proposed in reference 6. For optimization problem, the idea of extragradient was first used in reference 7, which proposed an extended extragradient method, EEG, by combining this idea with some first-order descent methods. The updated rules of EEG method are as equation 5. Intuitively, EEG allows us to examine the geometry of the problem and consider its curvature information, which is one of the most important bottlenecks for first-order methods. Therefore, we introduced the idea of extragradient used in EEG into ISTA to improve it. Next, we give the proposed process of our ELISTA. Firstly, we introduce the idea of EEG into LISTA and obtain the update rules as equation 6. Then, in order to reduce the number of learnable parameters and establish the connection between the 2 steps of equation 6, we make the following changes to W1t and W2t. Next, inspired by reference 8, we further reduce the number of learnable parameters by change Wt to W. Finally, we obtained the following extragradient-based LISTA-E-LISTA, whose updated rules are as equation 7. According to the updated rules of ELISTA, we get the network structure diagram of one layer of ELISTA as shown in Figure 2. After getting the network structure of ELISTA, we find that it is very similar to the structure of ResNet. When we regard Y as a known bias, the network structure of ELISTA is completely consistent with ResNet. The comparison between the two is shown in Figure 3. Therefore, we established the relationship between our ELISTA and the ResNet with excellent performance in deep learning. We also provide the proof of convergence of ELISTA. To prove the convergence of ELISTA, we first need a basic assumption as expressed in assumption 1. With this assumption and some other definitions, we finally get the conclusion that ELISTA can achieve linear convergence, which is shown as Theorem 1. Besides, we conduct a lot of experiments to verify the effectiveness of our algorithm. Firstly, we compare our ELISTA with the state-of-the-art methods LISTA, LAMP, and GLISTA based on synthetic data with different settings, including different SNR and different condition numbers of ill-conditioned matrices A. We set M equal to 250, N equal to 500, and T equal to 16. For the method of data synthesis, both dictionary A and X star obey standard Gaussian distribution. The sparsity of X star is realized by Bernoulli distribution with a probability of 0.1. Y is generated by A and X star and active white Gaussian noise epsilon. The experimental results as shown are shown in Table 2, from which we can see that our ELISTA can achieve the best results under different settings. In addition, in order to verify the effect of our algorithm in practice, we compare our ELISTA with the state-of-the-art methods LISTA and GLISTA for 3D geometry recovery with photometric stereo. And the tests are performed using the 32-bit HDR grayscale images of objects bunny as in reference 16 to 18 with Q equal to 35, 25, and 15. And 40% of the elements of the sparse noise E are non-zero. The results of the experiment are shown in Table 3, from which we can see that our ELISTA has better performance. Finally, we draw some conclusions about our work. In our work, we propose a novel extragradient-based learned iterative shrinkage thresholding algorithm called ELISTA with interpretable residual structure. And we also prove that ELISTA can achieve linear convergence. Moreover, extensive experimental results verified the high efficiency of our method. This could have both radical and practical impacts to the relationship between new neural network architectures and advanced algorithms, and potentially deepen our understanding to interpretability of deep learning models. However, one limitation of our work is that in theoretical analysis, we use the same assumption as in the previous work, such as LISTA, CPSS, ALISTA, and GLISTA, that the sparsity of X star is small enough. Removing this common assumption is our future work. Finally, here is the reference for this report. And that's all for my report. Thanks for listening.